Welcome to the Freefall post activity. Yesterday we did a wonderful little lab where we dropped all these picket fences through photo gates to measure their acceleration. And there were 3 questions that we wanted to answer. And that was, in each case, we were looking at freefall, which we've defined as falling under the influence of gravity only, no air resistance or anything else. So our first question was, is it uniformly accelerated motion? Well, that was answered probably 27 different times when you looked at the resulting velocity time graph. In each case, it was a diagonal, straight, very linear line, usually a correlation of 1. Since we defined the acceleration as being the slope of a velocity time graph, and since the slope is constant, that means that yes, indeed, free fall is uniformly accelerated motion. So free fall is in fact a motion just like a cart moving down an incline. In fact, traditionally, this is the way that Galileo actually studied free fall. Not having high-tech instruments like we do, he wanted to slow down the motion of free fall. So realizing that it was a uniformly accelerated motion, he actually looked at balls rolling down steeper and steeper inclines, and in that way kind of looked at what free fall would be even without dropping something and actually finding free fall. The second question was, now that we know that it is uniformly accelerated, is there a particular number? And certainly looking at your labs, there is a particular number. And that number is so important that it's given its very own symbol and its very own name. It's called a lowercase g, and its value is negative 9.8 meters per second squared. And this is what is known as the acceleration due to gravity, or the free fall acceleration, near the surface of the Earth. Now notice I'm only guaranteeing this number where we did the lab, near the surface of the Earth. If we were to drop something on the moon, it's actually about 1/6 as fast. So the acceleration on the moon is about negative 1.6 meters per second every second. Now you might be looking at this number and saying, hey, wait a minute, didn't we already have a 9.8? And didn't we already have a 9.8 that we called little g? Indeed we did. Right? We had little g as 9.8 newtons per kilogram, which was the gravitational field strength near the surface of the Earth. And this was the amount of force of gravity that was applied to any kilogram of mass near the surface of the Earth. So the Earth creates a gravitational field around it, and if you put a kilogram of mass in that field, it gets 9.8 newtons of force put upon it by that field. And it's not a coincidence that these two numbers are the same, but we do need a little more physics, one more unit, and then we'll be able to look at why these numbers worked out to be the same. So it's no fluke that they gave it the same symbol. But notice it's different units. It's negative because it's downward, and the units are meters per second squared. It's an acceleration due to gravity. Now, what does this acceleration mean? Well, remember that meters per second squared are actually meters per second per second. And that might help you interpret that what this means is that this freely falling object increases its velocity 9.8 meters per second for every second that goes by. So if it starts from rest, after 1 second, it'll be going 9.8 meters per second downward. After 2 seconds, it'll be going 19.6 meters per second downward, and so on. Right? Every second, it'll go 9.8 meters per second faster. In fact, if you reverse it, throw something straight up in the air, it'll slow down 9.8 meters per second every second as it goes up, and speed up 9.8 meters per second for every second on its way down. So it's a very important little number. Our third question, what was the relationship between the mass and the acceleration of free fall? Well, you made a graph of acceleration versus mass, and all your graphs were pretty much horizontal lines, which means that when you change the mass, what effect did it have? None. This is what is called Galileo's law of falling bodies. Galileo was the first one to originally find that, and the legend is that he dropped objects, or bodies, if you will, off of the Leaning Tower of Pisa. There's no actual evidence that he ever did that experiment, but it's kind of one of the legends of physics. Galileo's law of falling bodies says in a vacuum, so again, if we have free fall so we can neglect air resistance, all objects fall with the same uniform acceleration regardless of mass. So in other words, as long as we can neglect air resistance, it doesn't matter whether something is really massive, a ball of lead, or whether something is less massive, a feather. They will all fall with the same acceleration. Now, you might find that hard to believe. I mean, even though we've seen it in the lab. So I'm going to do some demonstrations of that just in class where I can actually create a near vacuum and show you that kind of thing so that you can see it in person as well. But you have to believe the results of your lab here. We had masses that were more than 8 times as massive as others, and yet you ended up with the same acceleration. Now, since free fall has now been proven to be uniformly accelerated motion, the same equations that we used for one-dimensional uniformly accelerated motion work for free fall, are famous for kinematic equations. Now, generally, they're written in a slightly different version. Here they are. You'll notice that they're almost the same. There are 2 differences in these equations from the ones we used generally. Notice here that instead of x's, we used y's. Why y's? Because free fall is vertical. So these stand for final minus initial vertical position, or you could write it as delta y, the vertical displacement, the change in the vertical position. And then the other thing you'll notice is that instead of a for acceleration, we're using our g, which is our specific to free fall acceleration near the surface of the Earth. Right, so rather than it being just something we're not even sure what it is, it's a, we know that this is a special motion, free fall, and therefore has a special acceleration. So again, I've changed all of the x's to y's, and instead of a, we're putting in g. And we know automatically, it's just one of the givens in any free fall problem, that g stands for negative 9.8 meters per second squared. Negative because it always acts downward. Why does it act downward? Because gravity acts downward. So you're going to do some worksheets here where you will do a few problems using the kinematic equations and graphs and things like that, although nothing terribly complex yet. We're going to save the more complex free fall problems for a couple of units from now. But at least we'll look at how fast and how far things fall. So you're going to have to remember these kinematic equations as well, but they really are the original ones with just a couple of variations. And of course, you can always put them on your 3x5 card. So this ends the free fall post activity. I am going to attach a little movie from The Simpsons here, but I'll do that post-production, and you can watch it.
Discovered something very unusual at that museum. Oh my God, what? Well, if you drop a feather and a bowling ball in a vacuum, they'll fall at the same rate. You think you've seen it all in this job, and then something like that comes along.